Hey everyone, welcome to Dev and Analytics Stuff YouTube channel. Today we'll implement union find algorithm or disjoint set data structure. Traditionally, a set data structure has all unique values. This disjoint set data structure also has all the unique values, but it comes with some additional properties. For example, every value in disjoint set belongs to a subset, and every subset has a parent value. To give an example here, this 3 and 4 belongs to this subset. This 5, 6, 7, all of them belong to this subset. And as I mentioned, every subset has a parent value that represents that particular subset. So in this case, 3 is the representative of this subset, 5 is the representative of this subset. Along with that, disjoint set data structure has two crucial methods, find and union. This find method returns the parent of subset of X. So, for example, if you do find of 3, it will find which subset this 3 belongs to. So in this case, this subset, and it will return the parent of that particular subset. So in this case, the parent of this subset is 3, so it will return 3. And similarly, if you do find of 7, it will find to which subset this 7 belongs to, and it will return the parent of this particular subset. So find of 7 will be 5. It has one more method, union, or one more crucial method, union xy. So what this does is it does a union of subsets of x and y. So for example, if you do the union of 2 and 4, what it does is basically combines these two subsets and creates a big subset out of them and assigns one of them new parent. So earlier we had two different subsets, with one being parent of one subset and 3 being parent of another subset. Now we'll have only one parent. So let's just say in this case 1 stays the parent and 3 loses its parentship. So we'll cover following things in this video: the naive implementation of union find data structure that will have time complexity of big of n for both find and union operations. Then we'll try to optimize this time complexity by adding rank, which will make the time complexity to big O of log n. And then we'll try to optimize it even further by adding path compression, which will make the time complexity of find and union operations to close to big O of 1, that is constant time. And in the end, we'll discuss about how to use union find in graphs. Every subset in this union find data structure can be thought of as a tree, with the parent of this subset being the root of the tree and other values being the children nodes having pointers to their immediate parents. For example, in, in this subset, 3 will be the parent, with other values being the children node having pointers to 3 and 3 having a self pointer, noting that 3 is the overall parent of this subset. Relationship between root and children of a tree of subset can be represented programmatically using a map or dictionary. So now, let's say we have following operations on our union find data structure. Create subset 1. So we'll create the subset 1, with 1 being the parent as there are no other values in this subset. We'll create corresponding tree. Here again, the tree will be rooted at 1 as there is only one value in the subset and 1 is the parent, and we'll add the corresponding entry in the parents map. So what this parent map tells is the parent of 1 is 1. So similarly, we'll create subset 2. we'll add corresponding tree and the entry in parents map. Same goes for 3. We'll create tree rooted at 3 also. Now the find of 2 operation should give us the parent of the subset to which 2 belongs to. So it should return 2. The union 2, 3 should do the union of subsets to which 2 and 3 belong to. For example, in this case, uh, let me just combine these two subsets and let's assign 2 to be the parent of this particular subset. So parent of 3 will become 2 now. So parent of 3 will become 2, and similarly we'll do the corresponding changes here in the tree, whereas 3 will be pointing to 2. So union of 2 comma 3 is done. Now when you do find of 3, it should give you the parent of the subset to which 3 belongs to. So it will give you 2. So this will give you 2. Now when you do union of 1 and 3, so what you need to do is do the union of the subsets to which 1 and 3 belong to. So let's just do it in this case. Let me move it a little bit closer. And as always, every subset will have only one parent. So let's say in this case, 1 is assigned as a new parent. So we'll do the corresponding changes here also. We'll change the parent of 2 to be 1. So we are changing the parent of 2 to 1. So the union of 1 comma 3 is also complete, and eventually the parent of this subset is 1, and when you do find of 3, it will return you 1. Programmatically, when we have to do find of 3, we use this parents map. We find what's the parent of 3, it's 2. What's the parent of 2, it's 1. What's the parent of 1, it's 1. So we follow this process until there is a self parent in the parents map. So you can understand, in the worst case, if your tree is skewed like this, your find operation can take big of n time. And when you do union of 1 comma 3, you first find the parent of this subset to which 1 belongs to. Then you find the parent of the subset to which 3 belongs to. And then you combine these two subsets and make one of these two as a new parent. So this union operation is dependent on this find operation. And as the time complexity of find operation is big of n, the time complexity of union operation will also be big of n. So we'll look at the naive implementation of union find data structure in Java now. So as I mentioned before, we'll have a hash map that stores the value and its parent. So let's call it parents map. In the constructor, we'll initialize this parents map. We have a method called add subset. So what this method does is, if a value is present in parents map, then it doesn't do anything. But if the value is not present, then it creates a new subset, adds this new value to that subset, and makes the value self-parent. So that's what add subset method does. So now we'll talk about this find method of union find data structure. It checks which subset this value belongs to, and it returns the parent of that particular subset. Now let's take an example here. You have a parents map 3, 3, 1, 3. So what this basically means is, you have a subset of value 3 and 1, and 3 is the parent of that subset. So when you do find of 1, you loop over this parents map until this condition is not met. So the value should be equal to its parent. Until this condition is not met, you loop over this parents map. Now, let's talk about this union method. When you want to do union of value 1 and value 2, you check which groups or which subsets these values belongs to. You find their parents and make one of these two parents as the parent of the larger subset. The time complexity of find and union operation depends on what is the height of the tree. So if your tree is skewed like this, then height of the tree will be n. That means the time complexity of find and union will be big of n. But if your tree is well balanced like this, then the height of the tree will be log n, and your time complexity of find and union operations will be big of log n. So this is what we'll try to achieve using union by rank approach. Now let's understand how union by rank helps us in reducing the height of the tree. This algorithm has one more hash map called ranks map along with parents map. So this ranks map stores what is the current rank of a value, and rank you can assume it is similar to height of the tree rooted at that particular value. Now let's walk through this example. Create subset. Now this is quite similar to what we did before. We'll create a subset with one being parent. We'll create a tree with one being parent. We'll add the entries in both parents map and in ranks map. Now when we add a new subset, the rank of that new subset will be 0. Now same thing applies for 2 and 3. We'll add corresponding entries in parents map and ranks map. So these three operations are done. This operation find of 2 will return you 2. We don't really have to go through that. This union operation, union of 2 comma 3. Now let's look at that. This operation first checks what is the parent of 2 and what is the rank of 2. Rank of 2 is 0. Then it checks what is the parent of 3. Parent of 3 is 3. What is the rank of 3? The rank of 3 is 0. Now since in this case the rank of both the parents is same, it does not matter which parent becomes the overall parent of the new larger subset. Let me just combine these two subsets by making 2 as the parent. I have combined these two subsets to make the 2 as the parent. So I'll make corresponding changes in parents map as well. The parent of 3 has now become 2. And since we made 2 the new parent, we'll increase its rank. So we'll increase its rank from 0 to 1. Now when you do find of 3, it will give you 2. Now when we have to do union of 1 and 3, we'll first see what is the parent of 1, that is 1. We'll see what is the parent of 3, parent of 3 is 2. We'll see what is the rank of 1, rank of 1 is 0, the rank of 2 is 1. Now, since the rank of 2 is more, the new larger subset that will create, the parent will be 2, as the 2 has the higher rank. So let me just make 2 as the parent of the new larger subset. So now, as you can see, I have combined these two subsets to make 2 as the parent. The corresponding tree is also changed. And this time the tree is balanced. So the height of the tree is log of n. We'll also make the corresponding changes in parents map. So the parent of 1 will now become 2. The rank of 2 will change only when the two parents which we are trying to combine has the same rank. So in this case, the rank of 2 will stay as it is. Now we'll discuss the changes in union by rank approach. As mentioned before, along with parents map, we'll have one more hash map called ranks map, which will store the ranks of all the members. So we'll make changes to the constructor in which we'll initialize the ranks map. We'll also make a change in add subset method in which we'll assign the rank 0 to the new value that we added. We'll do some changes in union method. So as before, we'll find the parent of value 1, we'll find the parent of value 2, and if the rank of parent 1 is less, then we'll make parent 2 the new parent. Else, if the rank of parent 1 is more, then we'll make parent 1 the new parent. And if the rank of both parent 1 and parent 2 is same, then we can randomly assign one of them as a parent. In this case, I'm assigning parent 1 as the new parent, and also I'm increasing the rank of parent 1 by 1. So again, pay attention here. We are increasing the rank only when the ranks of both the parents is same. Let's consider this example. If you perform these set of operations, then eventually you'll get the parents map like this and ranks map like this. And the tree will be of this form. And let's say you want to perform find of 4 operation on this tree. What you will do, you'll first find who is the immediate parent of 4, you'll go to 3. Then you'll see who is the immediate parent of 3, you'll go here. And then you'll see who is the immediate parent of 1. Until this self parent is not found, you'll do the loop. Agreed, the time complexity of this will be log of n. But every time going through this log of n operations is not necessary, especially given that the link between 3 and 4 is of no use to us. So what we can do, when for the first time we find what is the parent of 4, we can update the parent of 4 to 1. So next time when we want to find what is the parent of 4, we can directly get the value 1 instead of going through this loop again. So that's what path compression is all about. In path compression, we'll be changing the parent of this 4 from 3 to 1. Also, when we do this, the overall time complexity of this find method changes from big O of log n to big O of alpha of n. This alpha is something called as inverse Ackermann function, and for integers its maximum value is 4, so we can assume that it is close to big O of 1. Now for path compression, the only change that we need to do in code is in this find method. So every time we find a parent for a particular member or value, we update the parents map with the new found parent and we return the new found parent. Union find data structure has many applications in graph. A graph can be represented as a union find data structure very easily. Every vertex or a node in a graph can be assumed as a member of this union find data structure, and every edge in a graph can be assumed as a union between these members. So this graph can be easily represented as this data structure using these set of operations. Now, the question asked us to find the number of connected components in this graph. So first thing we'll do is we'll convert this into the union find data structure, and then we'll try to find the number of unique parents these members have. So in this case, there are only 2 unique parents, 1 and 3. Hence, the number of connected components will be 2. Just like this, union find has many applications in graphs. If you like this video, then please hit the like button, share it with your friends, and subscribe to our channel.